It seems logically impossible that adding an infinite string of numbers together could result in anything other than an infinite total. Yet under specific mathematical conditions, these endless additions settle into a single, finite value. Consider the wall analogy. You start exactly 2 meters from a wall. Each step you take covers exactly half of the remaining distance. Your first step moves you 1 meter forward. Because you only ever cover half of what is left, your next steps are 0.5 meters, then 0.25, and so on. As you add these distances together, the sum inches closer to 2, but it can never exceed it. You are adding an infinite number of steps, but they are contained within a 2-meter limit. In this unit, we will learn the sum to infinity formula, used to calculate these limits precisely. We will use it to convert repeating decimals into fractions and solve a classic physics problem involving the total distance of a bouncing ball. To apply these tools, you simply need to identify 2 values, the first term, a, and the common ratio, r, which is the multiplier used to find each subsequent term in the sequence. Infinity is often treated as a vague concept, but in a geometric series, it is a measurable value, captured with exact mathematical rules. Let's examine a sequence where the terms shrink over time, 80, 40, 20, and 10. First, we identify our variables. The starting term, a, is 80. To find the common ratio, r, we see that 80 is multiplied by 0.5 to reach 40, so our ratio is 0.5. Before calculating a sum, we must verify that the series actually converges to a finite number. This only happens if the absolute value of the common ratio is strictly less than 1. If the ratio is equal to or greater than 1, the sequence diverges. In this example, where the ratio is 2, the terms grow larger with every step. Adding these up leads to an infinite total, so no finite sum exists. Our ratio of 0.5 is less than 1, so this series converges. Because the terms shrink toward 0, the total sum will stabilize at a specific value. This is the sum to infinity formula. We place our first term, 80, in the numerator. In the denominator, we subtract our ratio of 0.5 from 1. 1 minus 0.5 gives us 0.5. When we divide 80 by 0.5, we get a final sum of 160. Once the condition for convergence is met, an endless string of additions is reduced to a single predictable number. A repeating decimal is essentially an infinite series, a pattern that cycles forever without end. Take the decimal 0.54, repeating. We can deconstruct this into a series of separate addition blocks, 0.54 plus 0.0054 plus 0.000054. To use our formula, we convert these blocks into fractions. The first term, a, is 54 over 100. Since each subsequent block is shifted 2 decimal places, the common ratio, r, is 1 over 100. We plug these into the formula. In the denominator, 1 minus 1 over 100 leaves us with 99 over 100. To simplify, we multiply the numerator by the reciprocal of the denominator. The hundreds cancel out, leaving 54 over 99. Divided by 9, the fraction reduces to exactly 6/11. This demonstrates that repeating decimals are not mathematical outliers. They are geometric series with a perfectly clear fractional value. We can also apply this to physics. When a ball bounces, it loses a percentage of its energy and height with every impact. Suppose a ball is dropped from 10 meters and rebounds to 80% of its previous height on every bounce. If it could bounce forever, what is the total distance it travels? In this diagram, we have to distinguish between the drop and the bounces. The initial 10-meter drop only travels downward. However, for every subsequent bounce, the ball travels up to its new peak and then back down to the ground. We first calculate the sum of these peak heights. With a first bounce of 8 meters and a ratio of 0.8, the sum to infinity for these heights is 40 meters. Because each bounce represents both an upward and a downward trip, we multiply that 40-meter sum by 2, giving us 80 meters of total bounce travel. Finally, we add the initial 10-meter drop that started the process. 80 plus 10 gives us a total vertical distance of 90 meters. By isolating the components of the motion, we can determine the absolute boundaries of a physical process that theoretically never ends. You have now learned the mechanics required to define infinity. You can take a sequence that never stops and calculate its exact destination. To test this, consider a statement that often feels incorrect. that 0.9 repeating is exactly equal to 1. You can prove this using the formula. Take the first term as 0.9 and the common ratio as 0.1. Try plugging these values into the sum to infinity equation. By following the rules of convergence and the constant ratio, you can mathematically verify results that might otherwise seem impossible. Post your calculation in the comments to show the final result.